Welcome back. Hope you're doing well. Last time we were talking about continuity of functions. Essentially, how can we write functions in a way that they are all connected with each other? All of the points all can be connected in nice little ways. Of course, that was our intuitive understanding, but we learned a way to write this in terms of epsilons and deltas with our previous discussion. Before we move on to talking about derivatives, something that's going to be interesting and useful for us in the future is to know when functions have inverses. In particular, one of those kinds of instances might be when you have a continuous function and then that function is always strictly increasing or strictly decreasing, meaning that it is always going up or it is always going down in some sense. So we're going to talk about these types of functions a little bit today and make sure that we have concretized our definitions of these things that we are going to be calling monotonic functions. And while we're doing this, we'll also introduce what is known as the exponential function. We're going to be building these things from the ground up from our definitions. So the exponential function, the one that we're used to, we're going to be actually building it up and showing that this function actually works and has all of the properties that we want it to. So that's going to be a little bit of our discussion here today, but we're going to start off here by talking about monotonic functions. Now, monotonic functions are defined on some sort of domain and are either going to be non-decreasing, strictly increasing, non-increasing, or strictly decreasing. Now, some of these you can have more than one. For example, if you're strictly increasing, you're automatically non-decreasing. And if you're strictly decreasing, you're also automatically non-increasing. And you can see these definitions here. So just to make sure that we're clear on these, as there is some ambiguity on these definitions, depending on what textbook you're looking at, we're going to say that a function is non-decreasing if whenever you have 2 points inside of your domain, then increasing your x value does not decrease your y value. Increasing your x value does not increase your y value. So if x is less than y, f of x is less than or equal to f of y. Another way to write that is that f of x is not greater than f of y inside of its domain. Now, if we end up realizing that whenever you increase the x value, that the y value can only go up, it can't stay constant, then you would have something that is strictly increasing instead. So looking at some of these pictures here, you can think about what sorts of pictures you'd be having for each of these sorts of diagrams. Maybe you have something like this versus something like this. Right, the picture on the left here is going to be a non-decreasing function. But notice that it is not strictly increasing because there's a part of this function that indeed is constant. Any parts, if it has any constant part at all, then it cannot be a strictly increasing function. Whereas this one on the right here, you can see even though this one does not have a domain of all real numbers, this one is still strictly increasing. And because it is strictly increasing, we also know that it is non-decreasing. So the world of strictly increasing functions includes those that are, well, rather, the world of non-decreasing functions includes those that are strictly increasing, like in this sort of example here. So this is meant to kind of mitigate between what kinds of functions have, this sort of bijective property that we often look at whenever we're looking at inverses. In particular, monotonic functions are good places to start when looking at these things. Now, we can also go the other direction. We can say that a function f is non-increasing if whenever you increase your x, your y values do not go up. They only can go constant or they can go downward. They can only decrease or be constant. And strictly decreasing means that whenever you increase your x value, your y value is forced to go down between any other sorts of points there. Notice that none of these functions, there's nothing here that says that these functions have to be continuous in order for them to be defined in a specific way. So when I have something like this, I could write it as something like this, right here as something that's like a non-increasing function. Pretend that that little line down there is straight. And then decreasing functions can do something like this. They could just go like this and then go down like this. This one would be a strictly decreasing function. Now, notice that we're not trying to discuss this in terms of like where is a function increasing versus where is it decreasing. We're saying on its entire domain, it is increasing or decreasing. So for example, a non-example of all of this would be a function like 1 over x squared. This function, f of x equals 1 over x squared, is not increasing nor decreasing, at least in terms of how we're classifying this function. So it is neither. We're just going to say neither for now. We could say it's nothing, or we could say it is none of the above, or something like this. But f of x equals 1 over x squared is a non-example in this instance, because there's only a part of it that is increasing, and then later on it's decreasing. Another interesting example to kind of take in place for this, or another non-example, I should say, is something like this. We could be looking at a function like 1 over x. Or we could ask the question, is that by our definition, is f of x equal 1 over x decreasing? Well, if I look at this, I notice that it does seem to be going down everywhere that I'm going, and so I might be tempted to say yes. But looking on the domain of f of x equals 1 over x, I notice that there are actually 2 points that I can find where, as I increase this x value, the y values are actually going up. So indeed, this is not a decreasing function. So even though it has a negative derivative everywhere, which is one of the ways that we've sometimes been tempted to classify decreasing in the past, this is not a decreasing function whenever we're trying to discuss this. So non-decreasing, non-increasing functions, anything of this type is called a monotonic function. If they're just increasing strictly, we could add, if we needed to clarify, strictly increasing and decreasing functions are called strictly monotonic. So let's talk about what we know about some of these things. Any one-sided limit of a monotonic function exists. For example, you can't have something going on in terms of oscillation going in from one side on the line, because oscillation requires that your function continues to increase and decrease at a more and more rapid pace. But if we're saying that the function only increases, you can actually say, okay, at least one-sided limits exist. It's not necessarily true that limits have to exist everywhere, as we can see here with this example, but you can have one-sided limits, whichever direction that you're ending up going. Another theorem here, any monotonic function ends up only having one type of discontinuity. Remember that we said that oscillation is not going to work. So you can think about holes or something like this. If there's a removable discontinuity where it jumps up at some point, well, if it jumps up like a removable discontinuity, it has to come back down, right? So that is a jump discontinuity. So if you're calling that a removable discontinuity, that's good enough. But there's no hole, if you will, of that type in this function. It is only going to be jump discontinuities, much like what we see down here on this left graph. And then finally, a monotonic function that's defined on an interval is continuous if and only if. So we can talk about when a monotonic function is continuous. You can actually express its range as an interval whenever your monotonic function is continuous. So for example, you can look right here at the range of this function. The range of this function given here would be given as 0 to infinity, a whole interval. Note that using theorem 2 here, if this were not to be written as an interval, for example, then there would have to be a jump discontinuity. And because it is an increasing function, it would have to go up. And so there would be a gap in the range of this function that cannot be filled by any other point later on or beforehand in this function. Because of that, anytime that you have a continuous function, you must have that your image is an interval. And the opposite is also true. If your image is an interval, then you didn't have any jump discontinuities at all for very much the same type of reasoning. So your function had to be continuous since there are no discontinuities. Now, inverse functions are exactly what we want to be talking about when we discuss monotonic functions, because a lot of the functions that we want to be taking inverse functions of, very much like this top right graph right up here, are going to be those that are strictly increasing or strictly decreasing functions. So we're going to really want to talk about these. This one in particular, you can see that this is only the right half of something that might be thought of as f of x equals x squared. So if I wanted to find its inverse function, then I could just take this and flip it along the line y equals x and get the square root function instead. So whenever f is 1 to 1, which is strictly monotonic, and then we map it to its range so that it's surjective, we have an injective and a surjective map. We know that bijective maps have well-defined inverses, so we get everything that we need whenever we're looking at strictly monotonic functions. Now, we can actually say more. And whenever this function is monotonic, we can say a little bit more about what happens with this inverse function. Well, one, we know that if the function is continuous, then that image, that f of e that we're looking at, is itself an interval. So let's say, for example, that f is going from interval I to an image like f of I, where I here is going to be an interval. So if we have something like this, then we actually know f inverse is of the same type of function. It's now going from f of I to I, the interval I. In fact, we could say even more about this inverse function. If the function f is strictly monotonic, f inverse is also strictly monotonic and continuous on f of e as long as f is continuous. If we have those two things together for f, f inverse has the same properties. Let's see a little bit as to why this might be true. Well, continuous functions map intervals to intervals. What that means is that if you have, basically, we've talked about this with the intermediate value theorem, if you have an interval going from A to B, not only does it map the minimum and the maximum point to their respective points, but it maps every point in between those two to some point in that range as well. So the intermediate value theorem gets to guarantee us this first sentence. Now, the inverse function f inverse is strictly monotonic whenever f is strictly monotonic. To think about this one for a little bit, remember that we're saying, for example, if something is strictly increasing, that x implies x is less than y implies f of x is less than f of y. Now, if you think about this for a little bit, what does it mean for f inverse to be strictly monotonic? We're essentially saying that something like this is going to be true whenever you're looking at the converse of this statement also being true. These f of x and f of y, remember in f inverse, these are now in the domain of the function f inverse. So this is kind of our replacement for x and y whenever we're writing the definition of strictly monotonic in terms of f inverse. Well, we're actually saying that whenever you have f of x is less than f of y, you can turn around and say that x is less than y. That is now the y values for f inverse, right? So this is kind of saying f inverse of f of x is less than f inverse of f of y. So this is the kind of the reverse statement, the converse statement of what it means for something to be strictly increasing. And similarly, we could define strictly decreasing. So what's going on here? Why is it that the converse of this would be true? Well, you can start by trying to think about what happens if this statement is false. Then there would exist some pair x and y such that this is true, but this is not. Well, then that would actually break this statement right here. If this is not true for some x and y pair, right, then what happens is you're looking at two different x values, x and y, and x is now greater than y. Yet with that pair being x greater than y, you still have it being the case that f of x is less than f of y. That is actually would denote some sort of decrease in the function, which would be a contradiction. So it turns out that when you have one statement, you have the other. So that is the explanation behind this part of the proof. So by construction, f inverse maps the interval f of e onto the interval e, which implies that f inverse is continuous. That was an if and only if that we got to discuss from before. Some examples here of these sort of invertible functions. First, we want to make sure that we're looking at things that are strictly monotonic. So we start by analyzing the power function x to the n. Now, note that whenever we're trying to find these inverse functions, at least in this section, what we're emphasizing is that our functions are continuous. That is one of the two things that we want to have whenever we're looking at using that theorem from the previous slide, because that guarantees that f inverse is also continuous. So that's something that we want to be kind of discussing a little bit. The function f is continuous on R. Let's take a look at what that means. So we can use that first part here for that previous theorem. It is also strictly increasing on a particular interval. That particular interval being the interval going from 0 to infinity, including 0. And we can note that a range is going to be the same interval. Now, note that this actually, we could say a little bit more about this if n is odd. So we could start breaking this into cases. In the case that n is odd, f is strictly increasing on the entire real line. In the case when n is even, of course, we have functions like y equals x squared, where we have that it is neither strictly increasing nor strictly decreasing. Only on part of its domain is it strictly increasing or strictly decreasing. So this would be a similar case whenever n is even. So we can conclude that the inverse function f inverse of x, which we are going to denote as the nth root of x, is a well-defined function, at least on 0 to infinity whenever n is even, and on the entire real line whenever n is odd. So we have now a way to talk about inverse functions. Remember that the way that we define inverse functions is that it's f inverse of f of x gets us back to the identity function, as does f of f inverse of x. So whenever we're working with stranger functions, we can at least know that if you have something that is strictly monotonic and continuous, you can always form this f inverse, which is also strictly monotonic and continuous. And so there's some function here that satisfies this property. Power function is something that we're familiar with, but sine of x might be something that, well, we have to think about what that inverse function works. Sine of x, right, we have the function f is continuous on R, and at least not on its entire domain, but on part of its domain, it is strictly increasing. It maps the interval negative pi over 2 to pi over 2 to negative 1, 1. And now we have this idea of why we end up restricting the inverse function of sine of x to particular intervals. Because we only want the part of it that's going to be strictly increasing. That gives us something that is bijective to work with. So the inverse function, which we usually call arcsine, or sometimes you see this written as just the inverse function of sine, is a well-defined and continuous function on the interval going from negative 1 to 1. So these are some very popular examples that now we have guaranteed have a lot of neat properties that we want to be using whenever we're making these sorts of inverse functions. Now, something that is good for us to remember is how can we show that a function is strictly increasing? How can we do that with this example? Well, remember that we're trying to use this definition for something, say, is strictly increasing. So we're trying to use that x1 is less than x2 implies f of x1 is less than f of x2. Note that we are not using anything regarding the derivative whenever we're trying to prove that something is strictly increasing. Just like we saw with the f of x equals 1 over x example, you can have something that has a negative derivative everywhere, but is not a strictly decreasing function on its domain. So we want to be able to use this definition. So for example, if we were looking at the power function example of f of x being x to the n, then we would want to show that whenever you have x1 is less than x2, you want to be able to show that x of 1 to the n is less than x of 2 to the n, right? And you have to ask, okay, how am I going to show something like this? You might decide you want to show something like this inductively, right? For example, you might look at two values, x1 and x2, that are positive, and you might say, okay, well, let's say what happens when I take a look at comparing x1 and x2. Let's start by saying that these are both positive or non-negative and see what happens if I try and show that x1 squared is less than x2 squared. Well, there's a couple of ways to do this. One way is to kind of start trying to work backwards with this sort of thing, right? I could look and see I would need it to be the case that 0 is less than x2 squared minus x1 squared. So there's at least a way for me to be able to write this as x2 minus x1 times x2 plus x1. Well, it's not too hard to show that indeed, if x1 is less than x2, then see, there we go. If x1 is less than x2, then this is positive. And then if x1 and x2 are both greater than or equal to 0, then this is also positive. So that can be one way to go through and show that. Now, if I didn't want to use induction, in general, if I wanted to do this for x1 to the k less than x2 to the k, then I might remember that there is a difference of cubes, a difference of fourths, a difference of even fifths function that allows me to write x of 2 to the k minus x of 1 to the k in a particular way, right? Being able to factor out a copy of x2 minus x1 times a bunch of things over here. So you might want to, it might be good to kind of keep that in the mental cage as you're kind of working through this. And note that in particular, you're doing this whenever 0 is less than or equal to both of your numbers. And there might be something different that you might want to try whenever you have x of 1 just less than x of 2, and you're looking at an odd power here for whatever your function is going to be. So this is the way that we could go through and try and write this out and try and prove that something is strictly increasing in order to guarantee by our previous theorem that this has an inverse. Now let's move on from inverse functions for a little bit and take a look at exponential functions. Exponential functions we're going to want to invert for sure because exponentials give us a logarithm. Now sometimes you actually go the opposite direction whenever you're trying to define these things. You may have seen an approach to this where before you define an exponential function at all, you start by defining a logarithm. Right, so sometimes depending on where kind of our treatment goes, if we ever end up, for example, dealing with exponents later, then sometimes what you can do is you can just define the logarithm, the natural logarithm of a value at x, this is for x greater than 0, to be the integral from 1 to x of 1 over x dx. Oops, maybe it should say 1 over t dt. There we go. So depending on what your treatment is in terms of the logarithm, you might see this definition here. However, we're not going to use this definition, at least in this treatment of this. So this is a perfectly fine treatment, and then you can go through, prove that this is strictly increasing. You can prove that it is continuous, and then use the previous theorem to get an inverse function, and then show that that inverse function is the exponential function. But what we're going to do instead is we're going to define exponential functions first. And what we're going to do is not only just define e to the x, we're also going to be defining a to the x, a to any other value. But before we begin talking about a to the x, let's start by defining this in an inductive way, starting with the natural numbers as our powers. For example, writing things like a squared, a cubed, it makes a lot more sense. And it's something that we're introduced to earlier before we're given fractional or real powers. So let's start here with the natural numbers as our powers. The way that we define this is by induction. If you start with a to the 1, then that's just going to give you a. Then a to the n plus 1 is going to be whatever you got from the previous number, a to the n, multiplied times a. For example, a squared is a to the 1 times a, and we know that a to the 1 is a, so this is just a times a. A cubed, same thing. It's a squared, this value, times a. So here we can define a to the n inductively. What this does is that it says whenever I want to take the addition of two powers with the same base, then I could break that apart into two various things, a to the m times a to the n. And I can do that either by induction on m or n as a proof, or I can start trying to break apart a to the m plus n using this inductive formula until I get to the point where I need to be. Same thing when you have a product inside of your power. We could use this sort of inductive formula to help us out there. It's especially useful once we've proven this first equality here. Now, in the case of a not equal to 0, we are going to also define what happens whenever I take something and raise it to the 0 power. That's going to give me 1. And then now I can also define it on the negative integers by just saying that that's going to be 1 over a to the n. Now, we might ask, or might have asked, why is it that I actually end up defining these in this way? Well, you might have noticed from our definition up here that there are some very nice properties that we get from trying to define the exponential functions using this inductive form. And we would love it to be the case if this worked whenever you had any integer, not just natural number, to plug in for m and n here. And indeed, that's exactly what we're trying to do whenever we define a to the negative n to be 1 over a to the n. In this case, you get a to the n times a to the negative n is a to the n minus n, which is a to the 0, which we're defining to be 1. So now these sorts of properties are going to work very well whenever we have any integers to work with. So now we can define negative values, and it also works whenever we are subtracting and things like this. So now we have everything that we need for these properties to be true on any integer powers. Now, we also have a way to define this in terms of fractions, and that is going back into using the root functions that we were talking about before when discussing the power stuff. Remember that we define the root function to be the inverse function of the power function. So, for example, if I'm looking at something like m1 over n1, then whenever I'm looking at these two things and I'm taking a to the m1 and then square rooting that to the n1, it turns out that this also ends up working whenever I have a different way of expressing that fraction in terms of potentially not its simplest terms. What that means is that we can now make a well-defined definition for power functions or exponential functions where the exponent now could be a rational number. It could be a fraction m over n, where m and n are both natural numbers and the denominator is not equal to 0. So whenever r is equal to q, we can let a to the r be a to the m and then taken to the nth root whenever r can be written as that fraction. Thanks to lemma 4, this is something that's well defined. We'd have to ask, if you have two different ways to write the same fraction, is it the case that these things would actually end up equaling? And indeed, that's what we have here from lemma 4. Now, the reason that we end up writing things in this way is that lemma 5 tells us that the same two properties hold whenever I'm looking now at not just integers, but rational numbers as my powers, right? So you can check this, for example, to see, take a look at something like a to the 1/2 plus 1/2. right? So this is going to be, we are claiming that this is a to the 1/2 times a to the 1/2, which is the square root of a times the square root of a. If you multiply these two things together, you get a, which is a to the 1, which we've defined to be a. So that does end up working. That gets us what we need. So it's all kind of motivated by these two conditions here. If we continue onward and say, let's take a look at these powers here, it turns out that a to the r is always going to be greater than 1 when r is greater than 0, and a to the r is always positive, but less than 1 whenever your power is less than 0. And of course, we've defined a to the 0 to be 1. Now, this is only the case whenever I have a being a number itself that's greater than 1. We know that some of these inequalities flip whenever we're looking at, say, a number in between 0 and 1. For the base here for a. Now, exponential functions, we're now going to talk about how we can continue to build these things in terms of their rational numbers. And to do this, we're going to need the help of defining a function. We're going to define a function f sub a. And that function, the way that's going to be defined is that we are going to fix a base and then let r, the input of this, be the power. This is exactly what we're used to whenever we see f of x equals 2 to the x. But this time, notice, instead of using x, we're using r, and that's to remind us that for these particular functions, we are looking at rational numbers as our exponents, because we have not yet defined them for the real exponents, because it doesn't seem to make them a lot of intuitive sense what it means to say 2 to the pi, right? Like, it doesn't seem very intuitive how this sort of thing would work. But we want to still define this so that we can have a function that is now defined on the real numbers to the real numbers so that we can start taking inverses, right? Our inverses are not going to be defined on rational points, right? We want them to be essentially defined on the real numbers just for the sake of making it a little bit nicer for us. Now, lemma 7 says that a function f sub a is actually going to be strictly increasing, and it gives us a nice little idea as to why. What happens if r is greater than s, for example? Then I could take a look at this value, which is f of r minus f of s, a to the r minus a to the s. And it turns out that I could show that this thing is going to be positive. Here's how I would do it. A to the s I know is always positive whenever I'm taking a look at whatever this value is. We always know that a to any power, thanks to lemma 6 here, is going to be at least positive. And then we have a to the r minus s minus 1. Since r is greater than s, this value right here is going to be something that is greater than 0, and hence a to the r minus s is greater than 1. So if I subtract 1 from it, this is still positive. This value right here is still positive. So all of that stuff put together gives me that this thing is going to be a positive value. Another lemma that's useful for me is that whenever I take something and consider the power of n as it goes toward infinity, then the root of a to the n, the nth root of a is going to go toward 1. This is true for any finite number a that I'm plugging in, as long as a is going to be greater than 0. Now, I'm not only making that distinction of a being greater than or equal to 0, because we know that if we go into negative numbers, we're starting to look at square root of -1. We're starting to go into the world of imaginary numbers, right? And in those sorts of instances, it's not necessarily the case. So we want to make sure that we have a is greater than or equal to 0 for some of these things to work. In fact, I should be saying a is greater than 0, because we know that this would instead approach 0 if we had 0 to the nth root. Now, with these two lemmas together, we're going to try and show that we can define the real exponents here, so some irrational powers for these exponential functions, by starting by showing that their limits exist at these real numbers. So we're going to take the limit of rational numbers that approach some real number, potentially an irrational number. And we're going to show that this limit exists, whatever real number that you end up putting there. And our goal here is going to be to show that this value is exactly what we're going to define 2 to the pi to be, for example. It's going to be the limit, as we take a look at rational numbers approaching pi, of 2 to the cube. But in order to do that, we need to show that this limit exists. That is, regardless of what type of sequence of rational numbers I'm using to approach pi, whether it's increasing, decreasing, or some of both, I want to show that that limit exists. So that's exactly what I'm going to go to try to do. Well, by lemma 7, we know f sub a is monotonic. So we do have that the one-sided limits of this both exist. That's good news. That means at least we're not having to check for things on, things coming from the same side, if sequence-wise not being nice with each other. But we do need to show that these two sides of the limits exist, that L plus is equal to L minus. Here we're defining L plus to be the limit from the right and L minus to be the limit from the left. So let's choose a sequence of rational numbers here, such that we have c minus 1 over n is less than rn is less than c. So you can see that this sequence is approaching from the left for this sequence. And then s sub n is going to be a similar sequence that approaches from the right. In particular, we're going to define s sub n in terms of r sub n. We're going to define it to be r sub n plus 1 over n, so that the difference between these two sequences is exactly 1 over n. Well, we know a to the r sub n is going to approach the left-handed limit. A to the s sub n is going to approach the L plus limit. And the question is what's going to happen when I consider the differences between these two things? Well, we do have this thanks to our, excuse me, our previous lemma about what works whenever I have rational numbers. And I can take two things that are added, r to the n plus 1 over n, and I can break them up into two similar based powers multiplied together now. And I can start looking to see if these two things are identical. Well, right now, this is being multiplied times a to the 1 over n. So there's not quite identical, but they are at least very close to each other. How close to each other are they? Are they approaching the same point? Yes, they are, because lemma 8 tells us that a to the 1 over n approaches 1 whenever a is greater than 0. Excuse me, a is greater than 0. So lemma 8 gives us everything that we need. So now we can define for any irrational point the limit of all rational numbers going toward that irrational point. We know from our previous lemma that this is well defined. Now, we can breathe for a little bit because we've actually defined an exponential function. The exponential function now exists on the real numbers, not just the rational numbers, and can be given for any base that is positive here. Now we know a lot of things about this theorem too. We know that it is strictly decreasing. We know this because of the fact that it was increasing on the rational numbers and that the limits work nicely, kind of filling in the gaps for the irrational numbers. We know it's strictly increasing, that is, if a is greater than 1. It's strictly decreasing, we flip the idea, if a is in between 0 and 1, and it's a constant function if a is equal to 1. We also know from all of this that the function f sub a is continuous because even at the irrational points, we are defining the function to be the limit. And remember, that's a characterization of continuous for a function. And of course, it has the well-known condition that we have here, a to the x plus y equals a to the x times a to the y. And that's because even for irrational numbers, limits work well with products, as we know. So this kind of gives us a little bit of our idea of the proof. So the corollary of this is that we have a function that is strictly monotonic. We have a strictly monotonic and increasing or continuous function, which means we can apply our previous theorem. This gives us an inverse function for any exponential function as long as a is not equal to 1. No inverse function for a constant function. But this inverse function is defined to be log base a of x. So this is something that is well defined and continuous. Well, now we get to use these sorts of conditions and use everything as if we built it up ourselves because we have all of the proofs and stuff here ready to go. But that will do it for us today. We've been talking about inverse functions, how we know inverse functions exist, especially focusing on monotonic functions whenever we have these sorts of discussions. But that will do it for me today. Thank you so much. Have a wonderful day.